All right, class, welcome back. Let's get right into it. Next section we're looking at, 10.5, tangents and secants. We've got two more sections to go. This one and one more. We'll spend Monday and Tuesday, review on Wednesday, quest will be on Thursday, or I guess I should say test. We'll make it a test for chapter 10. That'll be on Thursday, okay, of next week. And then after that, we'll just spend the last week just looking at area, volume, that kind of stuff. So, all right. So, we're looking at here. Okay, so what is a tangent? Well, a tangent, besides the tangent ratio, okay, remember tangent was opposite over adjacent, but that's the ratio in a right triangle. There's also a line called a tangent. So, a tangent is a line that intersects a circle at one point. Okay, and only 1 point. So maybe we'll say exactly 1 point. And that's called the point of tangency. So if you notice, line AB is a tangent because it only intersects the circle, which is circle C, at 1 point. Okay? All right. So our one theorem we can say about tangents is that if a tangent intersects a circle at a radius, a right angle is formed. So notice, since line L intersects circle S at a radius, it makes a right angle. So that's one theorem I've seen before on like standardized tests. They throw random ones out there, but this one I've seen a couple times. Okay. So in example problems 1 and 2, we're going to use that idea that tangents to a radius make a right angle. So if you look at example problem 1, it says JL is a radius of J. Determine whether KL is tangent to J. So, again, right, either way, either it's going to be tangent either when a radius meets at a, when a radius and a tangent intersect, then it's going to make a right angle. In this problem, they're asking you whether it's tangent, okay? So we need to figure out whether it makes a right angle here. And how do we do that? Well, we have to ask, is this a right triangle? How do we know if something's a right triangle? Pythagorean theorem. So if you notice, from here to here is 8. We don't know this, but here to here is 8. That's a radius, okay? So now we need to figure out if this is a right triangle. So we'll say, well, let's use the Pythagorean theorem. Our question is 8 squared plus 15 squared. Does that equal 17 squared, the hypotenuse? We get 64 plus 225, okay? That equals 280, 17 squared is 289, and 289 is equal to 289. So yes, KL is tangent to circle J. Now, in example problem 2, it says find X. It should also say, this one could say assume lines that look like tangents are actually tangents. So that's one difference. Sometimes they'll tell you it's tangent, sometimes they won't tell you it's tangent. You just have to look. So in example 1, since KL is tangent, that means it intersects the circle at one point. In this problem, we're just going to assume that JH is a tangent line. So again, what does that mean? Well, we just said that tangents to a radius, GJ is definitely a radius. It goes from the center to the side of the circle. So that's going to be a right angle. And thus, we're going to make a right triangle. So now we can use Pythagorean theorem again to solve for x. We're trying to find x, which is the radius in this case. So we're going to say x squared plus 12 squared equals, well, what's the hypotenuse? Well, it's x plus 8, right? It's that whole line segment GH. So now we get x squared plus 144. That equals x squared plus 16x plus 64. And this becomes a problem that you've already done. In the past, the x squareds are going to cancel out. We get 144 equals 16x plus 64. Subtract 64 from both sides, and we get 80 equals 16x, and x equals 5. So again, the big takeaway there so far, tangents to a radius make a right angle, and tangents intersect a circle at one singular point. Okay, you're going to use that a lot in calculus. We'll use it, okay, and here just a little bit. Okay, our second theorem is also about tangents. So it says more than one line can be tangent to the same circle. So we can say if two line segments or lines are tangent to a circle and start at the same point, let me just say actually line segments here. If two line segments are tangent to a circle and start at the same point, those segments are congruent. Okay, so again, in this figure, we're going to apply this, assume lines that appear to be tangent or tangent. So since AB and BC both start at B, they're both tangent to the circle, we can say they're congruent. So again, if you look in example problem 3 and 4, again, in the book they usually say, assume that segments that appear to be tangent are tangent. So you can assume, you know, that I have to tell you to assume, okay? So in this one, you know, again, RQ and RS, they're tangent to the circle, and they both start at R, so they have to be congruent to each other. So we would just set them equal to each other. 3x plus 8 equals 26, 3x equals 18, and x equals 6. Okay. In the next problem over here, notice that we might have some work to do. So, well, what do we know? Well, we've got QR is a radius here, that's 4. QT is a radius here, that's 4. This line segment here is 4. Over here is x. This has to be x, okay, because both those SR and ST both start at S. They're both tangent to the circle, so they have to be congruent. Now, notice we'll also combine the last theorem, because if a tangent intersects at a radius, it makes a right angle. So now if we want to find x, well, again, we can use the Pythagorean theorem. We can say x squared plus 4 squared equals, in this case, 9 squared. So SQ would be the hypotenuse of both triangles there, but they're right triangles, so we can use the Pythagorean theorem. So we'll say x squared plus 16 equals 81, x squared equals 65, x equals the square root of 65, plus or minus. And of course, we only need to have a positive answer for one of the sides, okay? So notice we used both theorems there, right? Tangents to a circle that start at the same point are congruent, and tangents to a radius make right angles. Notice you might be saying, how come there's no right angles over here? Well, it's only when a tangent intersects a radius, right? So if I drew a line right here, then yes, this would be a right angle. But if I drew a line, you know, right here, or I don't know, something like that, or if you had a chord, right, if it was like this, there's no way to know that's a right angle, okay, because that's not the theorem. It's only a tangent to a radius makes a right angle, okay? All right. So in the second part here, we want to recall, okay, circumscribed polygons. Okay, so circumscribed polygons, polygon is circumscribed if the circle is touching, if you will, the polygon on all sides. So notice how circle J's quadrilateral TURS is circumscribed about, we would say, circle J. Notice all the sides are touching. All the sides of quadrilateral TURS are touching circle J. So we're going to use our theorems here, especially that last one we just talked about, which was tangents to the two tangents to the circle that start at the same point are congruent. So notice how in this problem, right, those two tangents start at point T. They have to be congruent. These two tangents here start at U. Those have to be congruent. These two tangents start at point R. They're congruent. And these 2 points, right, those two tangents start at S. Those have to be congruent. Okay? All right, so we want to find X, and I should say if the perimeter is, I don't know, I'll make a number up, 36. Find X if the perimeter of quadrilateral TURS is 36. So again, notice we applied the tangent theorem, and now we'll just find the perimeter, which would be 4x plus 12 equals 36, 4x equals 24, and x equals 6. Okay, in the next one, we want to find x and then the perimeter. So again, we know that tangents to a circle that's starting at the same point are congruent. So again, I'm going to look at this and say, well, QU and QT have to be congruent because they both start at Q. So 2x equals 14 and x equals 7. Now, I need the perimeter. Well, I know we've got 17 here on the bottom, so this is 17, but hey, since SV and ST both start at S, these have to be 17 inches both. And then that makes RV equal to 10, and hey, well, RV and RU are 10 because they both start at R in their tangents. Again, we can assume that things that look like tangents are tangents, or we're going to in this problem at least. All right, so now we've got 20. Those are the two in blue. We've got 34. Those are the two tangents in red. And in green, we're going to have 14 and 14. That would make 28. Okay? So that make 82 inches for the perimeter, and x is equal to 7. Okay? All right. And then the last problem we want to look, or the last part we want to look at a secant. So a secant is a line that intersects a circle at 2 points. So in example 7, lines J and K, our secants, and in this picture to the right, I'll let you write down what you think the secants are. So those would be lines CB and line DF, right? Because those both go through the circle 2 times. So notice, right, the difference between that and a tangent, this red line here would be a tangent, right? Because if I'm intersecting the circle only at point D, that's a tangent. The other lines are secants, they go through the circle at 2 points. Line CB goes through at point C and B, line DE goes through at D and E. Okay, so that's it. So on Monday, we're going to start with equations of circles, okay? And they go from there. So have a wonderful